Okay. Yeah, welcome everyone. Today I'm delighted to introduce Tanner Trickle, who's tuning in from Fermilab, where he's been a postdoc for the last few years, and I'm just learning that he's accepted a faculty position at UIUC, which is very exciting. So congratulations to him. But yeah, Tanner has been working on a lot of different aspects related to dark matter, but in particular, some very interesting work related to light dark matter, electron scattering, axions, and things like this. And today we're going to be hearing about dark matter detection with magnons. So thank you, Tanner, for taking time out to talk to us, and I'll hand over to you. Thanks.
Of course. Thanks so much for having me. I'm first of all glad I got the time correct. We had to do a little bit of a conversion there, so happy that I can talk with you guys at a reasonable hour here in Chicago. So yeah, as was said, today I'm going to talk to you about direct detection with magnons. And magnons, we'll talk about what they are, what it means to do direct detection. Um, And the big idea, the big picture of what I'm going to be talking about is really how can we use these low energy scale excitations to look for light dark matter. So we'll talk a little bit about the recent DOMIC results, but well-motivated models of light dark matter with mass above an MeV are currently being ruled out and searched for with electron-based experiments utilizing silicon and germanium targets. And typically those have energy thresholds on the scale of eV, and magnons are one type of excitation that we can utilize to search for dark matter that's even lighter than the MeV scale, all the way down to a keV. And so this idea actually was started with me and some collaborators back when I was at Caltech in 2019. And then we continued that work with also Andrea Metrodate in 2020. And then very recently with collaborators at Fermilab, we have a recent paper talking about how we can understand the magnon excitation rate in some magnetic materials using data from neutron scattering. And then there's a future paper to come out that's going to talk about quantum magnetics for axion dark matter. And today's talk is going to briefly use results from a lot of these papers, hopefully give you an idea of where we are and where we need to go in terms of using magnons for direct detection for light dark matter. So as a brief outline, what we're going to talk about is just generally where we're at with direct detection, and what we want to do, what we mean by direct detection, in case there's anyone who still doesn't know in this call. And we'll talk about what magnons are, why people are excited about magnons beyond the reasons that I was just talking about. And then we'll talk about light dark matter magnon scattering. So this is a process where light dark matter comes in and excites a magnon via a scattering event. We're going to talk about this calculation from a few different perspectives. We're going to first talk about a first principles calculation, where really detailed knowledge of the target is needed in order to understand the scattering rate very precisely in some of these materials, such as yttrium iron garnet or ferromagnets that you might want to use, targets that host magnons. And then we'll talk about how we can use a data-driven approach, which complements the first principles analysis. And this data-driven approach is using actual neutron scattering data from the MAP spectrometer at the ISIS muon, a neutron source. And then the last part of the talk, we're going to talk about a completely different type of signal and completely different dark matter candidate, which is the axion. And we'll talk about how axions can be absorbed into magnons. And specifically, we're going to talk about new types of devices that can search for these electron-coupled axions in parameter space that has so far been previously very underexplored. And we'll talk about how new advances in what's known as quantum magnonics can really help drive advancements here. So just to briefly get started, the goal here is to detect dark matter. We know that dark matter is 5 times more prevalent than ordinary matter, and we know that it makes up around 26% of the energy density of the universe. We know dark matter's gravitational properties all the way back to the cosmic microwave background, and have pieces of information from the cosmic microwave background all the way to today. But with astrophysical observations, we know the amount of dark matter that we have, but due to its gravitational interactions, we know how fast it's moving, and we know generally how strong it can interact with itself. What we don't know is how or if dark matter interacts with the standard model in any way. And so generally, to understand how we search for those interactions with the standard model, we draw this toy Feynman diagram shown here, where on the left side, we have two different dark matter states, and on the right-hand side, we have two different standard model states. Then the arrows going around this toy Feynman diagram show the flow of time. And so, for example, in a collider search, we smash together standard model particles and hope to see dark matter particles coming out, or at least see them as missing energy inside of our experiments. In indirect detection, we're waiting for a signal, generally from photons, of dark matter that's colliding in the center of the Milky Way, for example. And the photons that are generated by that interaction can be seen in telescopes, and we could indirectly infer the existence of dark matter. And then the last side of this diagram, where time is flowing up here, is direct detection, where we have a very sensitive detector that's built out of standard model particles. We're waiting for dark matter to come in and kick that detector in some way, leaving behind standard model particles in our experiment in a way that we can hopefully observe. And so today we're really going to be focused on this direct detection aspect of this Feynman diagram. And so I think it's a good time, especially now there have been some really fantastic advancements in direct detection. But I think the canonical direct detection experiment that everyone usually thinks of or comes to their mind first is a nuclear recoil-based experiment. So this is an experiment with tons worth of liquid xenon or liquid argon, liquid noble gases. And we put these tanks deep underground, and we wait very patiently in a very background-free environment for an incoming dark matter particle to come in and hit a nuclei, and that creates scintillating photons or electrons that we can see inside of these detectors. And generally, we understand the sensitivity of these detectors with this dark matter cross-section versus dark matter mass figure here on the right, where on the y-axis, we have the dark matter cross-section, which tells us how strongly dark matter interacts with nuclei. And on the x-axis, we have the dark matter mass in GeV. And in the dark gray shaded region here, we have this neutrino floor, or because of the audience I'm talking to today, it's probably more appropriately referred to as the neutrino fog. But the idea is that this is generally the region where atmospheric and solar neutrinos will act as a background in some of these experiments, and we'll no longer be able to understand and infer dark matter interaction cross sections that are smaller than this neutrino fog, neutrino floor. And the sensitivity of these nuclear recoil-based experiments has been dramatically improving over the past 20 years that we've been building, 20 plus years, 40-ish years that we've been building these detectors. And our current best exclusion region is shown in the light gray here. And this is excluded by the LZ experiment. And I think the recent Xenon 1-ton results, or Xenon N-ton results, excuse me, are at a similar level of cross-section. But you can see that they're getting very, very close to this neutrino fog. And building a better detector, which has more exposure and potentially lower backgrounds, that would be this ultimate WIMP, or ultimate weakly interacting massive particle dark matter search. And this specific experiment, has a lot of push, especially in the US, and building this ultimate WIMP dark matter search experiment was a major initiative in the recent P5 report. So it's a major goal for US particle physics over the next 10 years. And so I think it's safe to say that these experiments are well-funded, are going to continue doing the amazing science, looking for nuclear interactions for dark matter with heavier masses. And there's already interesting results in complementary areas of science where they can look for, actually those neutrinos themselves. And as you can see, the exclusion bound almost overlaps that solar neutrino floor on the left-hand side. And last year, they've already seen a few solar neutrino events in some of their detectors. So these detectors, once they reach the neutrino fog, neutrino floor, may be able to do very interesting neutrino physics as well. And so all of these detectors have a fundamental limitation in the dark matter masses that they're sensitive to. For example, here in the LZ exclusion region, we see that these detectors are not sensitive to dark matter with mass less than 10 GeV. And this is because the energy transfer to the nuclei becomes very inefficient. If dark matter is heavier than the nuclei, it's very good at putting energy into the detector at a level above the threshold energy of these sensors. However, if dark matter is much lighter, it no longer efficiently kicks the nuclei, and the nuclei just don't scintillate enough electrons, scintillate enough photons for them to be seen. And so there's a fundamental limitation in what these detectors can do. And so that is where the next generation of direct detection experiments, or really, I probably should say current generation of direct detection experiments, is really focused on. Looking for dark matter standard model interactions at masses much less than the GeV scale. And there were some fantastic results just a few weeks ago from the DOMIC collaboration. And so on this left figure here on the y-axis, we're showing the electron interaction cross-section. And on the x-axis, we're showing the dark matter mass. And you can see that the DOMIC experiments, SENSEI, Super CDMS, all of these experiments are using silicon and dominantly silicon. Some are using germanium targets. And the idea is that instead of waiting for a nuclear recoil to happen, we're waiting for an electron to be excited from a valence to a conduction band. And the exciting result that DOMIC just got was they were able to push their sensitivity below this Friesen line. And so this Friesen line is the line which corresponds to the couplings necessary to generate the relic abundance of dark matter from this electron interaction alone. So if there's no dark matter in the early universe, because dark matter interacts with electrons, some abundance of dark matter will be frozen in. The frozen in abundance will depend on the interaction cross-section. And so there's one interaction cross-section for a given mass, which is consistent with the observed amount of dark matter that we see today. And that line is shown as this blue Friesen line here. And you can see that the current DOMIC sensitivity reached below this Friesen line. And so it has ruled out a large part of the parameter space for essentially the simplest model of Friesen dark matter, where we have a light mediator mediating the exchange between the dark matter and the electrons, and dimension 4 operators on both the dark matter and standard model side. And so this was a very important benchmark for these experiments to hit. In some sense, this is why this whole direct detection with electron program was started, was to hit this Friesen line. And there's still a bit of work to do in the high mass end and also pushing to lower masses. But this is really a credit to all of the work that has been going on over the past 10, 15 years in improving the Skipper CCD technology. However, similar to the nuclear recoil, where we see that kinematics limits the lightest dark matter mass that these experiments are sensitive to, we have a similar limitation here for electron scattering. And you can see that, for example, DOMIC generally peaks around, or DOMIC starts to lose sensitivity for dark matter masses lighter than an MeV. And this is because if dark matter is non-relativistically scattering off of the target, if it has mass less than an MeV, it's going to have kinetic energy less than an EV, because the dark matter velocity is around 10 to the minus 3. And so that means for dark matter that's much lighter than an MeV, there's just not enough kinetic energy exchanged in the interaction to excite one of those electrons from a valence to a conduction band. And so this will be, again, a fundamental limitation to all of these experiments, even if they hit their exposure, even if they hit the exposures that they're searching for, this kilogram year, and they reduce down to 0 background counts in all of the electron bins. Fundamentally, they won't be able to probe dark matter lighter than an MeV. And as you can see here, even in this figure, that Friesen line still extends to the left. And fermionic dark matter can be heavier, can be as light as a keV. Generally, you want it to be a little bit heavier than 10 keV due to stellar cooling bounds. But there's a large part of parameter space where dark matter can be produced via the Friesen mechanism. And we need new experiments to be able to test that paradigm. And so if we want to
Sorry, can I ask you a
think about
question?
others. Oh, I'm sorry. Yes,
And
please.
we go back to the previous slide about so is that blue line is when you, at least within this model, you're fixing the relic, or is it just an exchange of so
Yeah, so in
yeah,
the blue line, this is the interaction cross section you need to generate the observed relic abundance
all right.
today.
Okay, the relic is fixed. Okay, all right, thanks.
Yes. Yeah, of course. Great. Okay, so we want to think about other types of detectors. And so, as we saw before, right, a limiting feature in all of these detectors is the kinematics in terms of the dark matter mass that they're sensitive to. And one way to understand the kinematics more generally is to just think about what happens on the dark matter side of the process. So, if dark matter comes in with some velocity v and exchanges momentum q, then we know that the energy deposited to the system in the non-relativistic limit is this expression here on the left. And what's important about this expression is that we can bound this expression. So if we just take the inner product between the momentum transfer and the velocity to be maximal, we know that the energy deposited to the target has to be less than this inverted parabola, this QV max minus Q squared over 2m chi, where m chi is the dark matter mass and Q is the momentum transferred to the target. And we can understand this region as in this kinematic space, this omega versus Q kinematic space figure on the right here. And these gray regions correspond to the allowed kinematics of a scattering process. So, for example, dark matter with a mass of the GeV can deposit energy and momentum to the target that lies in the light gray triangular region. But dark matter that's much, much lighter, dark matter with mass of 10 keV, can only deposit energy and momentum in the smallest lower left triangle of this kinematic space in the darkest gray region. And so the goal here is to design experiments which can probe these kinematic spaces, right? And so we see that nuclear recoil, the kinematics of nuclear recoil tell us that they're only sensitive to dark matter masses of around a GeV, maybe lighter if you allow the threshold to go below a keV. And electronic transitions generally require energies above an eV in order to, again, kick an electron from the valence band to a conduction band. So we see that electron transitions are limited to masses at around an MeV. So what we need to find are excitations with energies less than an eV that are sensitive to momentum transfers in the eV to MeV, keV range. And one type of excitation that has gained a lot of popularity are single phonon excitations. And so phonons are quanta of lattice vibrations. They are really harmonic oscillations of each of the ions around their equilibrium position. And you can understand phonons in this as, pictorially and graphically in this figure on the left here. This is one specific phonon mode in a complicated crystal. You can also understand phonons kinematically. And so this on the right is a figure of the band structure of sapphire as an example. On the y-axis, we have the energy of the phonon modes. And on the x-axis, we have essentially the momentum in a band structure format that is much more familiar to condensed matter scientists and particle astrophysicists or dark matter phenomenologists. But essentially, the most important point here is that the gamma point shows the zero momentum point. And a lot of intuition for phonon modes can be gained from looking at the band structure near this gamma point. For example, we see that there are 3 phonon modes which have no energy and no momentum. And these are acoustic phonon modes. They have a linear dispersion relation for very small q. And these are just sound waves that travel through the material. At higher energies, there are gapped phonon modes. And these are known as optical phonon modes because they can respond in certain materials. They respond to light, and so they respond optically. And what's interesting is that different targets can have a very different set of phonon modes. The number of optical phonon modes is 3 times the number of atoms in the unit cell minus 3, which really just means that the more complicated your unit cell is, the bigger your unit cell is, the more phonon modes you have. And what's great about that is that the higher in energy you have phonon modes, if you're looking for dark matter which excites one of these phonon modes, the higher in energy they are, the higher the threshold of your experiment has to be. And so this idea to use phonons has gained a lot of traction recently. And there is one experiment, for example, the SPICE experiment. So there's a few different experiments. So phonons, phonons exist in both solid and liquid targets. And the Tesseract collaboration at Berkeley has two separate experiments currently ongoing using phonons as the main target. There's the Herald experiment, which is using liquid helium and looking for excitations of the sound waves inside of liquid helium, the acoustic phonon modes in liquid helium. And then there's also this SPICE experiment. And this SPICE experiment is going to look for phonons that are generated in a very cold, very quiet environment, and phonons that are generated in either sapphire or gallium arsenide or maybe a quartz target. And so the idea here is that dark matter comes in and excites one of these phonons that live in the 1 milli-electron volt to 100 milli-electron volt energy range. And then really the question is, how do you read out these phonons? There's a number of different ways. If a photon is generated, you can put a detector a little bit farther away, like is shown here on gallium arsenide. But the more popular choice right now is to use a transition edge sensor and wait for the phonon to ricochet around your target and then hit a transition edge sensor and break a Cooper pair. And so Cooper pair breaking energies are around the milli-electron volt energy scale. And so as long as the phonon that reaches the readout target, the TS in this case, has energy above the Cooper pair breaking energy, you can detect that phonon. And the experiment is currently being built, and they're working their way down to the thresholds that they need and then also the backgrounds that they need. But the big promise of these experiments is because you're using lower energy excitations, you can search for lighter dark matter. And that's shown in this figure on the right here, where the current direct detection bound, as we saw, is actually a little out of date. But the blue lines, the blue dashed lines, are the sensitivity for a kilogram year and no background electron-based experiment. We see that that sensitivity goes down to dark matter masses on the order of 1 MeV because of that band gap restriction. However, because phonon modes have much lower energies, you can go to much lower dark matter masses and probe the rest of that Friesen line that you want to for electron-based interactions. And so magnons are kind of the spin-dependent cousin of phonons. They're collective excitations inside of a medium. But instead of being quanta of lattice vibrations, where the spring constants, you can think of it as a simple, you can think of phonons as a simple harmonic oscillator, and the spring constants are set by the interatomic force constants inside of the lattice. For magnons, inside of a magnetic material, the Hamiltonian of the target is really a Heisenberg Hamiltonian. So the spins interact with some exchange matrix, and that causes torques on one spin to push the spin next to it, on the site next to it. And because there are these collective interactions between the magnons, they can precess and you can create collective excitation. And what's interesting about magnons is that even though the exchange interactions are coming from slightly different physics, they're not coming from actual electromagnetic interatomic force constants, they're coming from spin interactions inside of these magnets. Interestingly enough, the energy spectrum, the band gap of magnons fills a similar region as phonons, and you can understand the band structure in a similar way. So at the gamma point, there are these acoustic magnons, which have no energy at no momentum. And then the more complicated your material is, the more optical magnon modes you have inside of your target. And so, for example, this on the right is the band structure of that yttrium iron garnet target that I was talking about before, which will come up later. And there are 20 magnetic ions inside of the unit cell of Yig, and so there are 20 magnon modes. But because magnons are spin-dependent excitations, right? They're excitations in spin. The idea with using magnons instead of phonons to look for light-dark matter is that some models of light-dark matter might interact more strongly with spins. And so because magnons are spin-like excitations, we would expect dark matter to spin-dependent dark matter model to interact more strongly with a spin-dependent excitation than, for example, a charge-dependent excitation or a charge a model which has dominantly charge-dependent interactions, like a dark photon model. And so now we're going to talk about the actual light dark matter magnon scattering process and how we can use complementary ways to understand the excitation rate and therefore the sensitivity of a certain target to these interesting spin-dependent light dark matter models. And so maybe even more pictorially than I was just talking about, to give you some intuition of what happens in a phonon versus a magnon scattering event. If you have a spin-independent coupling, for example, via Lagrangian in the bottom left here, where there's a vector current on the dark matter side and a vector current on the electron side, this is a charge-like interaction. And so dominantly, you can get an intuitive picture of what's happening when the dark matter scatters off of the target, as the dark matter is sending in an electric field. And if you have oppositely charged ions inside of a unit cell, these oppositely charged ions are going to be pushed in opposite directions because of that electric field. And this is going to shake the ions, excuse me. And shaking of ions is exactly what phonons are, right? So I think this is a relatively intuitive picture for how spin-independent coupled or charge-coupled dark matter generates phonons inside of targets. And magnons are the complement in the sense that if you have a spin-dependent dark matter model, for example, the canonically chosen SD dark matter model, which is also looked at in nuclear recoil experiments, where you have the same dimension 4 interaction, but now you have a gamma mu, gamma 5 on both the dark matter side and the electron side. This interaction will dominantly exchange a magnetic field. Generally, the interaction Hamiltonian couples the spin of the dark matter to the spin of the electron. And when a magnetic field is exchanged versus an electric field, magnons are excited instead of phonons. And so we can understand this a bit more concretely, the dominance of magnons to phonon excitations, by looking at, again, this specific spin-dependent dark matter model where we have an axial vector current on the dark matter side and an axial vector current on the electron side. And so if you start with this interaction Lagrangian at high energies, at low energies, a number of different interactions will pop up in the low energy effective theory. And generally, this interaction can excite both phonons and magnons. However, because the leading interaction is a spin-spin interaction, magnons are dominantly generated. And so here we see, in terms of a projected reach for the couplings, that a magnon excitation can do much better than magnon excitations are much more likely to be produced than phonon excitations due to this interaction in a yttrium iron garnet target, or YIG. And this is 2 orders of magnitude in coupling, which means it's 4 orders of magnitude in rate. And so to put this in give you another perspective on this, this means that to have similar sensitivity with a phonon-based target, it needs to be 10,000 times as large as a target that is using magnon excitations, right? And so you would really need to scale up your experiment if you wanted to use phonons to look for this type of interaction. And so this is where magnons really shine through, searching for light spin-dependent dark matter models. Okay, and now we're going to talk a little bit about how the dark matter scattering rate is actually calculated. Again, starting with this first principles approach. And I think it's somewhat understandable, and there's an easy way to understand the scattering rate from first principles. Just because you don't have to worry about screening and other in-medium effects. Really, for a magnon interaction, all we're doing is using Fermi's golden rule to calculate an excitation rate. And so this Fermi's golden rule should look very familiar to you, at least each of the components. So inside of the delta function, the energy conserving delta function, omega q is the energy deposited to the target for a given momentum transfer. And nu and k are the quantum numbers of the magnons in these systems. So nu is the band number, and k labels the momentum within the first Brion zone. And omega nu k is the energies that lie along those band structures that we were talking about previously. And so to calculate the interaction rate, what we need to be able to do is we need to be able to understand how our system can go from a zero magnon state to a single magnon state due to some interaction Hamiltonian. And this interaction Hamiltonian, we can understand as depending on the electron spin. And really, you should think about this as something that's being derived from the high energy theory. So you have a UV theory at very high energy scales, then you can use effective field theory techniques to understand the low energy consequences. And any theory can kind of be any theory that generates magnons can be packaged down into this interaction Hamiltonian, where O is an operator and L and J here just sum over the different magnetic ions inside of your lattice. So I think it may show up again at some point. So L is indexing the unit cells, and J indexes the ions inside of the unit cells. And so this is really just an interaction which couples to all of the spins, all the electron spins in the same way in the target. And so that's really all we need for the particle physics side of the calculation. What we need to do now is actually understand how to calculate the matrix element of a zero to single magnon state with a spin operator sitting in the middle. That means that we need to know how to write the spin operator in terms of magnon raising and lowering operators to perform the commutations and actually get a precise scattering rate. And so in an analogous situation, the simplest situation, which you can think about doing something like this, right? Really, we have a Hamiltonian, just like a harmonic oscillator. We have a Hamiltonian that's written in terms of physical variables. For example, a simple harmonic oscillator, which is written in terms of momentum and position. And then we need to know how to diagonalize that Hamiltonian. We need to know the transformation between X and P in order to diagonalize the Hamiltonian in terms of the fundamental modes. And it's a similar Hamiltonian for the spin system, the Heisenberg Hamiltonian. It's similar in the sense that it's quadratic in the spins and the physical variables we care about. But it takes a slightly different form. And it takes a form where we're summing over all the different lattice sites and summing over the exchange interaction between the spins on each of the lattice sites. And the input to this target Hamiltonian really comes from this exchange matrix J, which can be fit from neutron scattering data. And this is a complementary way to use the data that we'll be talking about shortly. And so once we have this Heisenberg Hamiltonian, you can do some fun math with it and perform a Holstein-Primakov transformation and a Bogolov transformation to diagonalize the system. It's a fun exercise in quantum mechanics. But the point is that you can write the spins at each lattice site in terms of the magnon modes. And after you do that, you can calculate the excitation rate. And so the excitation rate that you want to calculate, the dark matter models that you want to calculate for, are ones which dominantly couple to spins in the low energy limit. And so here I'm showing 3 different examples of magnetic dipole dark matter, antipole dark matter, and pseudo-mediated dark matter. And here the solid lines are the sensitivity for these experiments with different threshold energies. And so the way you should be thinking about these experiments as an idealization is essentially swapping out the sapphire and gallium arsenide targets we were talking about before with the magnetic target YIG. And so now, instead of generating a phonon and then detecting that phonon, we're generating a magnon and detecting that magnon. And we'll talk about schemes of single magnon detection later. But this is the type of sensitivity such an experiment would award you. And there's no other experiments that can directly bound this parameter space. You really need to do a magnon-based experiment. One with phonons will not have anywhere near the same sensitivity. And so let me say this calculation was performed for that YIG target that we were talking about previously. However, other groups have performed these calculations for similar models. For example, the magnetic dipole dark matter model, where you use a different target. And so YIG is a ferrimagnet, similar to a ferromagnet. So there's a net spin associated with it. And there can be problems with that readout scheme that I was talking about before with phonons, because transition edge sensors don't really work well inside of external magnetic fields. And so you might be worried about putting a transition edge sensor onto a magnetic material. One way around that is to use antiferromagnets. And this nickel oxide is an antiferromagnet, which means it has no net magnetization. But because it has ordered spins, it still has magnons. It hosts magnons inside of it, and therefore it's sensitive to spin-dependent dark matter models. And here you can see for nickel oxide, manganese oxide, and then this other target, the sensitivity for single magnon excitations and also two magnon excitations, which was calculated with an effective field theory framework. And it's an interesting calculation that can generate you more sensitivity at the lightest dark matter masses due to kinematic reasons. A different target is a quasi 2D material. And the reason you might want to use a quasi 2D material, this is a 3D material, but generally it's very anisotropic in the sense that its structure is very layered. And this anisotropy grants you something special. It grants you a daily modulation. So you might be familiar with annual modulation effects in the nuclear recoil context. But what's exciting about these light dark matter experiments is that you can have this intrinsic anisotropy inside of the target. And that means that as the Earth rotates on its axis throughout the day, it sees the dark matter wind coming from a different direction at different times of the day. And this generates a daily modulation. This daily modulation can be used to discriminate against backgrounds. And generally, you lose sensitivity because of this, because you need a lot of events in order to tell that you have daily modulation inside of your system. However, you do gain sensitivity, even if you're background limited, because you don't expect your backgrounds to modulate on a daily basis. And so this was another calculation performed by some folks at Berkeley for this quasi 2D material target that I wanted to highlight. Okay, and then there's more theoretical work here. I was highlighting a few example models which really corresponds to a few specific high energy UV models. However, in general, we want to understand how these detectors respond to any type of dark matter model, and that's where effective field theory becomes very useful. And you can use what is a more complicated version of Fermi's golden rule and find the coefficients of the scattering. You can match the coefficients of the scattering potential to what shows up inside of your high energy theory. And so these C's that relate this, that determine the low energy scattering potential can be determined from the high energy theory. And I would point you to our recent work, or our work in 2020 on performing and understanding this effective field theory of dark matter direct detection with collective excitations for both magnons and phonons. Okay, and so now we're going to talk about the data-driven approach to the dark matter scattering rate. And so I want to begin by just noticing a similarity between this dark magnetic dipole moment dark matter model and the neutron, because the neutron dominantly interacts with electrons via a magnetic dipole moment. And so if the neutron, if you can understand the neutron scattering rate, essentially you would expect to be able to rescale the scattering rate to understand the dark matter scattering rate. And so the interaction structure between some of these spin-dependent dark matter models and neutron scattering is very favorable. Additionally, neutrons are excellent because they're heavy. And if they were moving at 10 to the minus 3 C, they would cover the kinematic range that you want to be able to cover for scattering. And so, for example, if a neutron, again, had speed 10 to the minus 3 C, you would be able to understand the target response for all omega Q sitting inside of this green shaded, or underneath this green shaded region. And so this is very powerful. This is probing the scattering kinematics where you want to, which isn't always done with electron-based experiments or photon-based experiments. And so really what is measured is what's known as this dynamic structure factor. And the idea is then to rewrite the dark matter rate in terms of the dynamic structure factor. So we can rewrite the total scattering rate on the left in terms of the measured dynamic structure factor on the right. And how do they actually do these experiments? This is a neutron spectrometer. And so many neutrons come out of a target, they're slowed down with water, and then they're chopped. And then you just fire neutrons at a target, and then you can scatter these neutrons off of a target and measure the angular distribution of the scattered neutrons. And that tells you directly what the scattering rate is. And so you can understand, so on the right here is actually a 2D slice of this data. Generally, you're given the data for 3 momentum directions and energy, and so that's a 4-dimensional parameter space. But you can slice it into momentum directions here, and these are actually the counts for a given momentum, for a given energy transfer. And what's nice about this picture is you can actually map contours of this data directly back to the actual geometry of the map spectrometer itself. And so this is real data that was collected to understand the magnon modes inside of YIG. And because we're interested in this YIG target, we wanted to directly use this data to calibrate dark matter scattering rates. And so in terms of our kinematic space, because the detector does not have full angular coverage and because the neutrons are actually moving a little bit slower, the kinematic coverage of the data itself does not cover the entire region it could, and it does not cover the entire kinematic region probed by different dark matter masses. And so some extrapolation is needed both in the magnitudes of momentum, where you want to understand the dynamic structure factor, and also in its angular information. So some extrapolations do need to be used for the data, but it's a pretty small region where you need to use these extrapolations. And what's exciting is that you can compare the data-driven results, so using the raw counts in the map spectrometer experiment, use those to calculate the rate and compare that to the Heisenberg model, which used the exchange interactions that were fit from the same data. And you find a very good agreement between these two different approaches. There's a bit of a discrepancy at high masses, but this is really where future work is going to help us understand what's going on here. There's 2 reasons both of these curves are probably a slight overestimate in the sensitivity, and that's because the first principles calculation, the Heisenberg model calculation, neglects magnetic form factors, which causes sensitivity to degrade at higher masses. And the data-driven approach probably has some phonon contribution at high momentum transfers. And so future calculations, by subtracting out the phonon contribution with more data, or performing the first principles calculations with magnetic form factors, included, will give us a much better understanding of the sensitivity at these 1 to 10 MeV dark matter masses. Okay, and there's much more to say about what dark matter models can be recasted, and how other targets, how the full spin-dependent response of other targets can be understood from neutron scattering experiments. But I'm going to move on to absorption, and please ask me about this later if you're curious. So now we're going to talk about a completely different type of signal, and that's from electron-coupled axions. So axions are very light dark matter. Generally, we expect their mass to be lower than an EV. And when they couple to electrons, if they have mass that is heavier than an EV, they can excite electrons inside of the solid state targets and noble liquid experiments. And the sensitivity of these experiments to this signal is shown here in the figure, in these figures. However, at low masses, there is currently no direct detection experiment that can operate and has sensitivity below stellar cooling bounds. And so this is very different than the situation we find ourselves in with axion physics for the photon coupling, where there's cavity haloscopes, there's a lot of ideas using collective excitations at very high masses, and other ideas, DM radio and things like this using LC circuits at very low masses. However, the axion electron coupling, the parameter space is a bit wide open in the sense that there's no experiment that's really reaching that QCD axion band that we would like to reach. And so I think now is a really good time to think about ways to search for the axion electron coupling specifically. And that's going to require thinking about targets, and specifically targets with spins in them, because in the non-relativistic limit of this axion interaction, generally what's generated are spin-dependent interactions. And so, for example, on the right-hand side, we see this axioelectric term. This is the term that's dominantly generating the electronic transitions at high energies. On the left-hand term, there's the axion wind contribution. And this is called the axion wind because the effective magnetic field that couples to spins depends on the gradient of the axion field. So it depends on the direction of the axion field is moving, or the axion wind. And so because we have a coupling to spins, electronic spins, we also know that we should have a coupling to magnons. And so in terms of a Feynman diagram, you can understand what's happening here. We have a linear interaction between the axion and the spins, and so the axion should be converting into a magnon. And this is somewhat analogous to the Caspar wind experiment, which is looking for nuclear spins changing due to the axion wind coupling to the nuclear spin. Here we are looking for magnons generated by coupling to the electric spin, electron spin. And so again, we can go through that same calculation from a first principles perspective that we were talking about before. We want to understand how to use Fermi's golden rule to calculate the transition rate between a single axion state to a single magnon state. The axion is generally being absorbed, so it's depositing its mass energy. And so for all of those magnon modes that we have in our system, we should expect a resonant response. However, the problem is that if you just calculate away, if you close your eyes and calculate, you find that the interaction rate is 0 for a target inside of no magnetic field. And that's because the interaction Hamiltonian, if it just depends on the sum over all the spins in the site, if the axion couples to all of the spins in the same way, this operator actually commutes with the Heisenberg Hamiltonian for simple targets, and you have a selection rule. So you can't actually absorb onto any of the higher optical magnon modes that we were talking about previously. However, there are ways around the selection rules. You can change your target Hamiltonian in 2 different ways. If you apply an external magnetic field that gaps these magnon modes and changes those commutation relations, and also gives you a handle on tuning your whole system, because now the shift in magnon frequencies is set by the external magnetic field. You can also use anisotropic exchange interactions, which again changes the target Hamiltonian to ruin those selection rules. And then you could also have an interaction where the spins in your system interact. The Heisenberg Hamiltonian describes the total spin dynamics of the system, whereas the axion only couples to the electron spin. And so non-degenerate Landé G factors introduce a different type of interaction on different sites. And so these are 3 different ways to break the degeneracy. And there, you can also understand the response in a data-driven way, because the response can actually be rewritten in terms of the target permeability, as shown in the bottom here. And this is similar to how a lot of dark photon searches, how the excitation rate of electrons, for example, for a dark photon search or an electron search can be rewritten in terms of the target dielectric function. Here, for a magnetic system, you can show that the rate can be rewritten in terms of the target magnetic permeability. And so you can use those 3 selection rules that I was talking about previously to understand the absorption rate in a few different targets. And we can see that if you can achieve a kilogram year exposure, which you know is something that can fit inside of a lab, it's about 10 centimeters cubed of target. If you can very sensitively read out such a device, you can have resonance sensitivity all the way down to these well-motivated QCD axion models where you also solve the strong CP problem. And so we focused again on a YIG target, and the collaboration and the people that were performing calculations of the antiferromagnets also performed calculations for nickel oxide and found similar sensitivity to the axion electron coupling, where you can dip down into the QCD axion band with enough exposure and low enough backgrounds. So now I want to briefly talk about how we actually read out magnons, because it's something I haven't touched upon in this talk. For phonons, again, the idea is they rattle around inside of your detector, they hit a transition edge sensor, and then they break a Cooper pair. And because Cooper pairs have energies of around a millielectron volt, they can be broken by a phonon that hits the transition edge sensor. However, if you want to read out single magnons, you can't really use a TES. And so you need to be able to read out a single magnon in another way. And so this is where overlap with quantum magnonics is a really promising approach. And the quantum in quantum really just because we're using a qubit or a two-state to read out magnons. So the high-level idea is if we have a magnon sitting inside of our target, if that target is coupled to some kind of qubit, then the magnon excitation can swap with the qubit excitation, and it can take us from a single magnon state and no qubit state, or de-excited qubit state, to a no magnon state and excited qubit state. And because we're getting really good and there's a lot of excitement about building high fidelity qubit systems, this seems like a promising way to perform single magnon readout. And on top of that, what's interesting is that qubits today generally operate in the 4 to 8 gigahertz region if you're talking about transmon qubits, but generally gigahertz frequencies are where qubits are operating today. And if we're thinking about absorbing axions, slightly lighter axions than the milli-electron-volt mass scale we were just talking about, those axions also resonate and have frequencies at the gigahertz scale. And so the magnons that are generated can also be at the gigahertz scale. And so you have a nice kinematic matching between the magnons inside of your target and the qubit. And so this idea was recently funded under the Quantum Information Science Enabled Discovery 2.0 grant. And the idea here is basically what I was saying. The idea is we have a lot of Yig spheres, and we wait for a magnon to be excited inside of these Yig spheres. And then we couple these Yig spheres by a superconducting resonator to a qubit, and then interrogate the qubit system and see if a magnon was generated or not. And this is one way you can do single magnon detection that can get you below standard quantum limited linear amplification readout schemes, and may also give you sensitivity to dark matter that scatters into magnons via a down conversion. And so what's interesting about this setup, and I think, we've already talked about how dramatically different targets can be used to search for dramatically different dark matter models. Even on the readout side, there's a lot of different types of qubit architectures and qubit technologies. And so because you want qubits which operate inside of an external magnetic field, transmons really don't cut it. And working with people at Notre Dame, they're actually developing what's known as electron-on-neon qubits. And so this is using the lowest two states of a system where an electron is trapped to the surface of solid neon. The lowest two states of those systems act as your qubit system, and they're resilient to external magnetic fields. And so you can multiplex this whole setup and tile this whole setup inside of an external magnetic field to get large exposures, potentially large backgrounds, and do single magnon counting relevant for both axion dark matter and more generally spin dependent beyond the standard model of physics. And so that down conversion I was talking about, recently I've also been working on a similar idea for phonons. So the idea is to perform single phonon counting with qubits, so coupling the phonons inside of a high overtone bulk acoustic resonator to a piezoelectric, then the piezoelectric couples to a transmon qubit, and then you can read out the qubit state to measure single phonon excitation. And there you can also look for signals which resonantly excite the phonon modes. However, if you want to look for dark matter scattering events, you might hope to be able to see this down conversion, this down converted shower. So you make a high energy phonon, and then that high energy phonon kind of showers down to lower energy phonons, gets into the phonon mode you're interrogating, and then gets into your qubit so you can do counting. We're thinking about a similar idea for magnons. So if you take this picture, change the target with a Yig sphere and change the phonon label with a magnon, that is kind of the idea if you want to use such a detector as a low threshold detector for light spin dependent dark matter. And so in summary, magnons overall are exceptionally sensitive to spin dependent dark matter. Neutron scattering provides a complementary new way to calibrate and understand the dark matter response to spin dependent interactions. And quantum magnonics is a very promising approach for single magnon readout. Thank you very much.
Thank you. Questions for Tanner? So I'll start while you're thinking. So, could you say a few words about what, for example, the axion search with where you would scan the magnetic field. You referred to the background, but you didn't mention what the backgrounds are in these sorts of experiments. What are
Yeah,
the sort of other effects which could excite magnons and stuff in these sort of systems?
yeah, that's a great question. So typically you're thinking about these systems being cooled to very, very low temperatures. So specifically 10 millikelvin temperatures. And when you're at that low of temperatures and looking at gigahertz and above frequencies, the energies are generally much larger than the temperature of the system. And so there are not really a large population of thermal magnons, and generally you expect to be able to cool this system almost to a ground state. And so the backgrounds are not really coming from magnons inside of the system. Where the main backgrounds are actually coming from now are the readout mechanism, because this reading out a qubit is not perfect. They can only perform the readout, and by readout, I just mean they're only able to count how many times a transition from the 0 to the 1 state inside of the qubit happens with some finite fidelity. And so it's really that single shot fidelity that hurts you, because that looks like a dark count background. And then other problems that you have in your qubit, there's quasi-particle poisoning, and other slightly athermal effects that make your qubit look like it's operating at slightly higher temperatures than it actually is. And so you also have to worry about the qubit thermals as well as the magnon thermals. But right now, I think this technology is really limited by the qubits that we have available, and really limited just by the dark counts in single magnon detection. Similar, and I think it's a similar story to how single photon axion detection that wants to utilize single photon detection above the gigahertz frequencies is limited by dark counts in their single photon detectors.
So would you say the projections for these axion searches that were done previous to this, assuming reasonable background conditions, or you think there's a bit of a way to go before those would
Yeah,
be
yeah,
possible?
we're certainly very far from reaching these numbers
Mhm.
here. So, but there's you so you so this line you can think of as being if you have a kilogram year and only thermal backgrounds, right? If you can actually reduce your dark count probability, uh, and that you're basically never going to get to the peak sensitivity. However, you'll notice generally there's a trend to have better sensitivity at slightly lower masses. And the gigahertz frequencies are at a bit slightly lower masses. And so actually what we're thinking of in this proposal is to focus more on the micro EV to 100 micro EV mass range, where the sensitivity is a bit better. And you we're still working through the numbers here, but you can get much. So let me actually go back to the other competing experiments, these other ferromagnetic haloscopes. With a reasonable amount of target material, with the dark counts that we expect today, we expect to be able to get below the red giant bounds. If you sit on resonance, and then scanning sensitivity can get below xenon n-ton. And that is with about less than a kilogram of material put in a dilution refrigerator that you can buy today, right? And the main advantages that you're getting from this system relative to these previous ferromagnetic haloscopes is the ability to scale. So these previous ones were using Yig spheres inside of a cavity. And so if you want to go to higher masses or lower masses, you generally need to change the dimensions of your cavity to get a good coupling. And so you can't really scale the system. It's difficult. Um, and they were also using linear amplification for their readout. And so there's some point where the dark count the dark count probability for a given measurement becomes low enough that you actually beat the standard quantum limit. And we're almost there with current detectors that have been demonstrated. And so you can get sub SQL and scale, and that's really what's buying you sensitivity relative to these other ferromagnetic haloscopes.
Uh,
Another
Dipan.
question?
Yeah, so I have a question about the spin independent and the spin dependent. limits from the magnon and phonon. So if you had a hit, and if you had both in a term, if you had both spin dependent and spin dependent, could you, in some region of parameter space, could you ever distinguish a phonon from a magnon hit? Or like, can you, in other words, can you disentangle the spin dependent and the spin dependent parts?
Good. The answer, I think it would be difficult with one target. I think it would be much easier with multiple targets. For example, you can look, I don't want to say this. Magnons don't exist in every target, right? Not every target is
Right.
magnetic. And so if you look for excitations inside of one target, which is magnetic, you can compare that to a similar target, which might have similar atomic masses and have a similar architecture at an atomic level. And you can look at the backgrounds in both of these systems and do a difference calculation, right? Also, there's different, and this is also where daily modulation comes into play and being able to understand the sensitivity, right? The magnons pick out a specific direction, right? And a ferromagnet, you have a magnetization in a certain direction. You could imagine changing that magnetization, reorienting the target, looking at daily modulation, and things like this to kind of shake your setup enough and check consistency with different setups to be able to disentangle what you're seeing.
Okay. Okay. Yeah. Probably a difficult thing to do, but I mean, it's
Yeah. Yeah. Definitely. This is this is also very very early days here in terms of where we're getting to the point where we can measure single phonons, right? And what I'm talking about now with this quantum magnetics is really the first iteration of an idea to do single magnon detection. And so this is very much just the beginning of this, and it's really hopefully telling us that there's parameter space available if we want to build these experiments. And there's interesting things that we can do with magnons, and we should try to push farther forward. Yeah.
Can I ask a question?
Sure.
So, yeah, like I wanted to ask, does the size of the object play any role? Because, like, for example, in axion experiments, like, the Broglie wavelengths of the axions is much larger than the target. So, in some sense, I guess that's kind of crucial for these experiments because they are kind of collectively exciting stuff. But here, are you looking just as non-collective excitations or how? Yeah.
Yeah. That's a great question. So let me say it like this: you're always exciting a collective excitation, even if you have a very long wavelength mode. So in terms of a band structure, you can think of the long wavelength axion perturbation as basically perfectly vertical. There's no momentum being transferred, but there's a lot of energy being transferred into the target. And that's exciting one of these modes at the gamma point, or k is equal to 0. In a scattering event, you're now exciting a collective mode, but the collective mode has some momentum transfer to it, right? It has a non-zero k vector inside the first Brion zone, and so it's not just a perfect in-phase precession of all of the spins. It is a slightly out-of-phase precession that's dependent on the momentum being deposited inside of the scattering event. So you don't always need coherence. For a scattering event, you don't need coherence across the whole sample to generate a collective excitation. But that is what's happening for an axion. And yeah, absolutely. I mean, and that's, again, let me say this actually. That is also what's setting this this selection rule. So it's really because the axion field here in the bottom left equation has no dependence on the site that you're actually at, because it's such a long wavelength field. If there was some site dependence, which you expect there to be because it should be a plane wave, so it should be e to the iqx, really there's corrections to this selection rule at the order of the momentum transfer, and generally you would expect those to be suppressed because that scales like the axion velocity, which is small.
I see. So for long wavelength, you have this selection rule basically.
Yeah, absolutely. And that's why you have this. It basically looks like a uniform magnetic field, and it's hard to create spins that shake kind of. So another interesting way to think about it is optical phonons are really out of phase oscillations because one ion is moving in one direction, one ion is moving in the other direction. Optical magnons are similar, but now it's the spins are precessing opposite of each other. And you can imagine that it's very difficult to get spins in different lattice sites to operate to precess in opposite directions with the same magnetic field hitting both of them, right? So that's why there's the e to the IQX suppression there.
I see. For phonons, does the same happen, or is it different? Like if
Or
like
for
can you explain?
phonons,
Yeah.
yeah, because they're oppositely charged ions, even kind of in a static electric field, they're still moving in opposite directions. So that's why you can absorb directly into phonons. And phonons, I don't have the figures here, but phonons are also a fantastic probe of dark photon coupled dark matter because you can absorb directly to those phonon modes. And it's interestingly enough, you can also use phonons to look for photon coupled axions if you can put your detector inside of a magnetic field because then you convert to an electric field, absorb into a phonon mode at the resonant frequency of those phonons, and actually generate some pretty good sensitivity in only a Tesla of magnetic field.
Okay, thank you.
Yeah, thanks for your question.
Okay, any further questions? I just wanted to ask quickly. I mean, it's just on the actual material itself, this yig. I mean, you were talking at some point you needing a target, which is sort of a kilogram, and then in your final slides, you were sort of showing these they were more sort of like 100, I guess, 100 micron spheres or something. So,
Yeah,
is this something
yeah.
to
So
do with the
these
fabrication of these things?
yeah. So this sphere specifically is about a milligram in mass, and so you need a million of these, but uh, you can tile these up into wafers, and so so you can scale up the mass generally about a factor of 1,000 if you want to put it all inside of one dilution refrigerator. But this is really only limited by the Yig spheres so the Quack's experiment also used Yig spheres and they're used the same mass. Like there's no reason you can't buy Yig, which is not in a sphere, or just buy more Yig, right? And so, yes, if you had a gram-sized Yig, which is not actually that much bigger because it scales like the size of it cubed, uh, you can get to that kilogram exposure with only 1,000 of those, right? Uh, and you can also get that exposure from different experiments. I mean, this costs much more money, right? But uh, one interesting point that I haven't touched on because we're still working on the details. This system here, we're as a first analysis, we're really only focusing on counting individual spheres. And this is kind of like incoherently adding the signal in all of these spheres. And so the SNR doesn't scale as rapidly with the number of spheres as you might expect because you're doing that. So on the bad side, your SNR is not increasing as fast as maybe you would want it to. On the good side, it means that you can put the spheres anywhere you want. They don't have to be, for example, within the coherence length of the axion field. If you had multiple experiments running outside of a coherence length, the sensitivity that we're going to put out in this paper will kind of be independent of that. And it's an interesting question moving forward to understand, kind of what the best design here is. And it's what you probably want to optimize for is as much mass in Yig sphere as you can get on a given site, measured the least amount of times to reduce the number of dark count errors in each measurement.
All right, yeah, great. Let me